Hello everyone and welcome to this training session on actuarial common entrance test. As a part of this subject, we are going to deal with the subject of mathematical foundation and the chapter which I am going to look at right now is the second part of the algebra. Of course, as a part of your subject, algebra is dealt as one single chapter itself, but because of the size, I have broken it into two. And in the first part, if you remember, we have covered areas relating to indices, logarithms, simultaneous equations, quadratic equations, and inequalities. Now, in this chapter, we'll cover the remaining aspects of algebra which are covered as a part of this curriculum. Something dealing with the progressions, the binomial theorem expansions, and even concepts relating to arithmetic mean, geometric mean, etc. All right, so let's get into our topics. So the first one which we are going to handle here is the arithmetic mean and the geometric mean. As we all know, arithmetic mean is nothing but a simple average. So all of you must be knowing how to calculate the arithmetic mean. It is nothing but the total sum of the numbers by the total number of numbers. Whereas when I talk about the geometric mean, this is slightly different from arithmetic mean. Instead of adding all the numbers, I take the product of all the numbers, I multiply all the numbers. Instead of dividing them by the total number, I will do to the power of 1 by the total number. So if I'm talking about A, B, C, the arithmetic mean will become A plus B plus C divided by 3, whereas geometric mean will become A into B into C to the power 1 by 3. And geometric mean is very powerful, especially in trying to find out the average, especially when there is a compounding that is involved, or the growth rate kind of things are involved. Wherever there is something associated with compounding, which is nothing but the previous value also being added for the next value. So that is where whenever we have a compounding kind of a scenario, we will take the average as a geometric average or a geometric mean compared to the arithmetic mean. And what we also see is geometric mean is always less than or equal to the arithmetic mean. So this is more and more conservative average, whereas this becomes more and more aggressive. And why did I use less than or equal to? They will be equal when all these are exactly same. When A equal to B equal to C, then it really doesn't matter whether I'm using an arithmetic mean or a geometric mean. Both of them will give me the same solution. Right? So some problems with respect to arithmetic mean, some numericals with respect to arithmetic mean and geometric mean are some of the things you people need to be comfortable with, because from this exam standpoint, this becomes one of the key areas of focus for us. Then the next thing is notation. A series of numbers, let's say something like this, a series of numbers can be written using their corresponding sum and product notations. If they are additions, I should be able to write them in the form of sigma. If there are in terms of multiplications, I should be able to write them in the form of pi. Let's see how we write them. Okay, if so before we start writing some of our examples, I'll take simple ones. 1 plus 2 plus 3 plus so on up to 10. The way I will write it is sigma I equal to 1 to 10 I. It means I will take values 1, 2, 3, 4, so on up to 10, and each one is added to itself. So it means first I will become 1. So which means 1. Because there is a sigma, there will be a plus. Now I will take the next value 2. Because there is a sigma, another plus 3. I will go on up to 10. So it becomes 1 plus 2 plus 3 plus so on up to 10. That's the way it should work out. Now, so that's the way we should try to express all these numbers also. So here, let's say I'll start off with the first one. 2 plus 5 plus 10 plus so on up to 226. I can write this. So you just think of what are these. So 2, I will write it as 1 square plus 1. Then I will write 5 as 2 squared plus 1. You need to be comfortable with some of the series like this. Then I'll write this as 3 squared plus 1. So you see there is a pattern. The last one I will write it as 15 squared plus 1. So how do I write it in the same? So what is changing here? Only this part is changing. 1, 2, 3 up to 15 is what is becoming, and there is a summation. So I will write it as sigma I equal to 1 to 15. Only that part is changing. I squared plus 1. Not I squared plus I, because the second part is not changing. Second part is a constant 1 itself. So I will write it as sigma I equal to 1 to 15 I squared plus 1. In this case, what is becoming? First I will take 1. So it becomes 1 squared plus 1, 2, which is the first term. Then I will take 2 squared plus 1, 5, which is the second term, and so on. So writing this form, you need to be comfortable playing around with the number patterns. Right? This kind of a number pattern, I should be able to express it in such a way that it forms some kind of a series. And how do I identify that kind of thing coming up? Just with some kind of practice, you practice various kinds of series, you will get immediate ideas in terms of what is the kind of relationship. Especially if you see the differences, here it is 3, here it is 5. The difference is keeping on growing. If the difference is keeping on growing, there is some level of thought that you can do whether there is any possibility of a square or a cube kind of thing that comes out into this kind of equation. Alright, let's try practicing the next one here. 2 plus 4 plus 8 plus so on up to 2 power 2n. Oh, he has already given the pattern. He is saying 2 power 2n. So now you know. Okay, so the first one is 2 power 1, 2 squared, 2 cubed. So this power is changing. Until how long it is going? It's going up to 2n from 1. So you know that I can very well write it as I equal to 1 to 2n 2 power I, because it becomes I equal to 1, I equal to 2, so on up to 2n. So this is the expansion for this is the sigma notation for this. Now what about this? Here also he has given the last term 2n plus 1. So this one also, okay, the first term is n equal to 1. So 1 by 2 plus 1, 3. This is n equal to 2, this is n equal to 3, and this is n equal to n. So this also I know I equal to 1 to n, 1 by 2n plus 1. So I put 1, I get 1 by 3, 2, I get 1 by 5, I get the second term, and all of them are added. Now look at this one, minus 4 plus 9 minus 14 plus so on plus 99. Okay, first thing is there is an alternate minus and plus. So whenever you see an alternate minus and plus, you should try out minus 1 to the power n. Right? Minus 1 to the power n or minus 1 to the power I. Okay, because if I equal to 1 it becomes minus, if I equal to 2 it becomes plus, I equal to 3 it becomes minus. So that is one aspect here. Now if I ignore the sign, it is nothing but 4 plus 9 plus 14, because minus 1 to the power I is taking care of that, plus 99. So the first term for me should be 4, the second term should be 9, third term should be 14. How do I think of that? First term should be 4, okay, and with a difference of 5. 5 is a constant difference, so I cannot think of a squared kind of a relation in this. So it should be more in terms of the first degree itself. So I am trying to keep it as 5y minus 1. Whatever is the constant difference, I am writing it as a part of the I multiplier. And because I need the first term as 4, I am making an adjustment of minus 1 so that it creates a 4 for me. So if that's the case, 99, 5 into 20 minus 1. So I can very well write it down as I equal to 1 to 20 minus 1 to the power I into 5i minus 1. Just think about this. Wherever I have an alternating minus and plus, first follow this, remove that sign, and then go ahead with your original numbers and see that how do you replicate. And here you are seeing that the differences are not changing, differences are constant, 5 itself. So whatever is the difference, try multiplying it with I. So it becomes 5i. But if I put I equal to 1, I get 5. I won't get 4. So that's the reason I have made a subtraction of minus 1 to create it as 4. And now when I substitute 2, I get 10 minus 1, 9, and so on. This is one way we should be comfortable in writing any expansion in terms of its corresponding sigma or pi, because all of them are talking about additions. I am able to write them in the form of a sigma notation, but if they represent multiplication, I should be able to write them in the form of a pi notation itself. Okay, let's look at some of the multiplications that I have taken below. 3 into 5 into 7 up to 2n plus 1. Now you see, when I put n equal to 1, 2 plus 1, 3. That's the first term. N equal to 2, 5. N equal to 3 is 7. So n equal to n, it becomes 2n plus 1. So because there is a multiplication, I put pi I equal to 1 to n 2n plus 1. So the first one looks very straightforward. Then what about the second one? E squared, e cubed to e power 2n plus 3. 1, 2, 3, so on. So again, this also becomes pi I equal to 1 to 2n plus 3 e power I. Here also it is 2i plus 1. Then what about the last one? 1 by 4, 1 by 9, 1 by 16. So I can write this like this. 1 by 2 squared alpha, 1 by 3 squared alpha squared, 1 by 4 squared alpha cube, and the last one I can write it as 1 by 16 squared alpha power 15. Now what is the kind of pattern you are seeing? You just see pi I equal to 1 to 15, 1 by, it's starting with 2, it's not starting with 1. So I will say I plus 1 whole squared and alpha power I. Now or probably, yeah, alpha power I. So now try expanding it, you will get exactly the same. So you should be able to convert the normal expansions in the form of sum and product. Identify the patterns, and once you identify the pattern, you can easily convert it. So that's the level of comfort you should get as a part of some of the expansion. So this chapter also focuses on you getting some level of clarity in terms of expressing a big series in the form of sigma and pi notations. All right. Now, The next context which we are going to look at here is the progressions. Progression is nothing but a series of values. Just like what we have observed in this case, we are talking about progressions which are a series of values. And that series, if I see that the differences are constant between the values, if the differences are constant between each of the values, we say that it is an arithmetic progression like 3 plus 5 plus 7 plus 9. The differences are constant between each of these values. Then we say it's an arithmetic progression. And if the ratios are constant, let's say 3 plus 3 squared plus 3 cube plus 3 power 4, differences are not constant. 3 minus 9 minus 3 is 6, 27 minus 9 is 18. So here the differences are not constant, but ratio, this divided by this is equal to 3. This divided by this is equal to 3. This divided by this is equal to 3. Where the ratios are constant, we say that it is a geometric progression. Where the difference, so we are talking of series. Series where the differences are constant, we call that series to be an arithmetic progression. Where the ratios are constant, we call that as the geometric progression. And as a part of our various calculations, we come across, for these kind of data, the questions can come out for us as, the first thing is find the nth term of this. Find the nth term of this arithmetic progression. So probably find the 10th term, find the 20th term. So whenever any series is given to us, first of all we need to identify or probably break it into an arithmetic or a geometric progression. The first step. If I am able to break it into an arithmetic progression, my nth term is directly found out using this formula, a plus n minus 1 into d, where a is the first term of that series. Let's say 3, 5, 7, 9 and so on. Now here the first term of the series is 3. That is what is a. And the d is whichever is the common difference between the two, which is 2. So if someone asks me to find out the 20th term of this series, it's nothing but a plus n minus 1, 19 into d2, which is giving me 41 is the 20th term of this particular series. That is what if it is an AP, arithmetic progression. But if it is a geometric progression, let's say 2, 4, 8, 16, and I want to find out the 20th term, then also the same logic. Then I will say that my 20th term is a, because this is a geometric progression. The ratio is constant, r. What is r? Whatever is the ratio between the two consecutive numbers, r is 2. So a first term is 2 into r to the power of n minus 1, 2 into 2 to the power of 19, and using our law of indices, x power a into x power b, x power a plus b. So this can be written as 2 to the power of 20 also. So my questions could very well be a series given, and for that series I would be asked to find out the nth term of the series. So depending on whether it is an arithmetic progression or a geometric progression, I'll use the formula either a plus n minus 1 into d or a into r to the power of n minus 1. Any of these expansions is what I'll typically use to find out the nth term of that particular series. Then there could be some other questions which will talk about not the nth term, but the sum of all the n terms. The sum of all the n terms of the series. So let's say 3, 5, 7, 9. This is the series. And there is a question that may ask, find the sum of the first 20 terms. So if I have to find out the sum of the first 20 terms, the formula can go like this. N by 2, which is 20 by 2, 10, into 2a, which is the first term. 2a is 6, a is 3, so 2a plus n minus 1, 19. 20 terms is what I required, so n minus 1 is 19 and d is 2. So it becomes 10 into 6 plus 38. So 44 into 10, 440 is the sum of first 20 terms of this series. So probably instead of adding 3 plus 5 plus 7 plus 9, if there is a pattern which is an arithmetic progression pattern in the data, I can apply this formula n by 2 into 2a plus n minus 1 into d to find out the sum of the first n terms of this particular series. Similarly, if it is a geometric series, let's say again 2, 4, 8, 16. Again the same logic, right? I can very well find out the sum of the first 20 terms using this formula. A 2 into 1 minus r to the power of n, 2 to the power of 20 divided by 1 minus 2, which is minus 2. So you can solve this and whatever comes out is the sum of the first 20 terms of this series. So depending on, if you are not able to express it in the form of AM arithmetic progression or a geometric progression, there is nothing much you can do. You have to simply add up each term. But if you are able to identify a pattern in the series saying that this is an arithmetic series or this is a geometric series, you can use these formulas to typically find out the sum of the first n terms of that series, or find out the nth term of that series also. So even if the series does not look that straightforward for you, you should be able to convert it into a series which is more straightforward, and then find out your nth term or some of the n terms of that particular series. And then we are talking of sum of infinite terms. Sometimes in a geometric progression, there could be a possibility of sum of infinite terms. Let's say 1 by 2, 1 by 4, 1 by 8 and so on. So let's say not the 20th term, but I'll say some of the infinite terms of the geometric series. So I know first of all this is a geometric series because the ratio is constant. 1 by 4 by 1 by 2 will give me 1 by 2, so the ratio is 1 by 2. So in this case, nth term you know how to find out, a into 1 minus r power n by 1 minus r. But if someone asks me about find the sum of infinite terms of this series, then it gets simplified to a upon 1 minus r. So a is 1 by 2 by 1 minus 1 by 2, which is 1 by 2. So this sums out to 1, which means all these infinite terms will sum up to value equal to 1. And remember, this formula a upon 1 minus r will work only when the absolute value of r is less than 1 itself. So mod r is less than 1. Only in this case, this formula is applicable, which means the value should be decreasing and decreasing and decreasing. If the absolute value of r is greater than 1, then this formula is not applicable and the values do not converge at all. So the output will always, the summation will always be equal to infinite. If they are coming down and down, we say that there is a convergence. And whenever there is a convergence, there is a possibility to find out the sum of the infinite terms of the geometric progression. For arithmetic progression, there is no such scenario of convergence, but only in a geometric progression we can try to find out the sum of the infinite terms. For an arithmetic progression, I cannot find out the sum of the infinite terms of that arithmetic progression. Alright? Okay? And there are certain common standard formulas which you have to be comfortable with. The sum of the first n natural numbers, 1 plus 2 plus 3 up to so on up to n. Right from 1, if it says, then this summation, probably you can test it out using your formula of n by 2 into 2a plus n minus 1 into d, but it will work out to n into n plus 1 by 2. That the last value into, so if I say first 10 terms, sum of the first 10 natural numbers, I can simply write it as 10 into 11 by 2, making it as 55, which is nothing but 1 plus 2 plus 3 plus so on up to 10 will give me a value equal to 55 itself. Similarly, sum of the squares of first n natural numbers will give me n into n plus 1 into 2n plus 1 by 6. So first 10 natural numbers, 10 into 11 into 21 by 6, 1 squared plus 2 squared plus 3 squared, so on up to 10 squared will work out to be this particular number. Okay, 2 3s and 2 5s, 3 1s, 3 7s. So 35, 11, 385 is the sum of the squares of the first n natural numbers. Then sometimes if someone says cubes, 1 cube plus 2 cube plus 3 cube plus so on up to n cube, then this works out to whatever you got through n square of that. So 55 square directly. So 55 squared, which works out to 3025. That's the sum of the cubes of the first n natural numbers. So these are some of the things which you should be comfortable with. Some of the n natural numbers, some of the squares of the n natural numbers, some of the cubes of the n natural numbers. Now you see the formula that is given here also for some of the cubes. I can very well write it as n into n plus 1 by 2 whole squared. That is what is 1 by 4 into n squared into n plus 1 by n plus 1 whole squared. So you can very well find out sum of the first n natural numbers and then square it and make it sum of the cubes of the first n natural numbers. So these are some of the standard summations you should be comfortable with. Alright. And one more thing that is covered as a part of this chapter is the binomial expansion. Binomial is especially when you have two terms, raise it to some power, you want to find out the expansion of that. It's a straightforward stuff. It goes like, so probably you must be knowing a plus b whole squared is a squared plus b squared plus 2ab, or a plus b whole cube comes out to a cube plus 3a squared b plus 3ab squared plus b cube. So these are one or two common expansion, but if you have a plus b to the power 8, then that becomes slightly difficult. So that is where I use this concept of binomial expansion to help me out. All I do is simply like this. So we talk about a plus b whole power n. So the first thing is we start with nc0, nc1, nc2, so on up to ncn. This is one part of this expansion. Then take the first term and put the last power, a power n. Then for each of them attach one lesser of that, a power n minus 1, a power n minus 2, then a power 0. And for the second term, start from 0 and start increasing, b power 1, b power 2, so on. Then join all of them with a plus sign. So there are three parts in this. The first part is for each of them. So let's say I want to find out, I'll take an example for you. I'll say I want to find out a plus b to the power 5. The simple way I'll work it out is, first I'll start with 5c0, 5c1, or probably I'll put pluses directly. Plus 5c2. I'm keeping spaces because I have to fill it with something else. 5c3, 5c4, and plus 5c5. So I'm using all right from 5, 0, 1, 2, 3. Take the first term a. Start with the highest power. So whatever is the first term, start with the highest power. 5. Make it 4 here. Make it 3 here. Make it 2 here. Make it 1 here. Don't make it anything, which is like make it 0. A power 0 is 1. Now take the second term. Start with 0. B power 0 anyhow is 1. B power 1. B squared. B power 2. Put B cube. Put B power 4. Put B power 5. This is what is the expansion. And you know how do you calculate this pi C1? NCR is nothing but n factorial by n minus r factorial into r factorial, or even in your scientific calculators you directly see this is the formula for NCR. So you just need to provide n and r values and it will give you the value of NCR itself. Okay, so let's take one practical example, and that is where things will be more easier for you. So let me try doing this. So this will work as long as the power is a positive integer. As long as the power is a positive integer, this mechanism will work. So 2 minus 3x to the power 7. Just look at it. 2 minus 3x to the power 7. Let me take a white sheet, a blank sheet where we can work it out. So let's say if I say 2 minus 3x to the power 7. Now as I said, because it is 7, 7c0 plus 7c1. So once you get a practice, you don't need to do like this, but just to get, until you get that practice, I'm giving you this mechanism. Plus 7c3 plus 7c4 plus 7c5 plus 7c6 plus 7c7. Okay. The first term 2. 2 power 7, 2 power 6, 2 power 5, 2 power 4, 2 cube, 2 squared, 2 power 1 and 2 power 0. Now the second term minus 3x. So minus 3x to the power 0 minus 3x minus 3x squared minus 3x cube minus 3x to the power 4 minus 3x to the power 5 minus 3x to the power 6 minus 3x to the power 7. Now the most common question is, okay, they will ask for find the coefficient, let's say of x to the power of 3 in the expansion. So where will I get x to the power of 3? So obviously this is just x to the power of 0, which is 1. Here I'll get x. This is x squared. This is the one that is x to the power of 3. So what is the coefficient for that? 7c3. Find out the value for that. 2 to the power of 4 and minus 3x to the power 3. So minus 3 to the power 3 is also the coefficient. So you do this simplification and say this is the coefficient of x cube in the expansion of this term. Now you don't need to put this entire thing. Now you just see where will you get x cube. So here there is no x possible. Only here there is a possibility of x cube. And if you see this number is matching with this number. So what you can very well do is, okay, when I put this to the power 3, this is what is going to give me x cubed term. So what you can do is 7c3 minus 3x to the power 3. And then what will be the first term? You just see, okay, 7c0 means 2 power 7, which is nothing but the subtraction between these two. So I'll write it as 2 to the power 4. So this will be the expansion of the, this would be the coefficient of x cube in the expansion of this. So let me try to give you one more example that makes it easier for you to understand this numerical. So now if I say find the coefficient of a to the power of 4 in the expansion 2a plus 5b to the power 6. Okay, I need a to the power of 4. So for 6c0, a will be 6. 6c1, a to the power of 5. 6c2, a to the power of 4. Okay, so I need the 6c2. The first term is 2a to the power of 4 and the second term will be 5b to the power of 2. Now you find out 6c2, you find out 2 to the power of 4, you find out 25, pi squared 25. Multiply all those things and you say that that is the coefficient. So the most common question for us is find out the coefficient of something in the expansion of this. So if you are able to expand it using, especially when your powers are positive integers, you can very well use this mechanism to find out the coefficient of a particular term in the expansion. But what if the power is not a positive power? What if the power is a fraction or it is a negative power? Now, in that case, there is a slightly different expansion. You write it in this form. Always any number, you expand it in the form of 1 plus x to the power n. Always write it as 1 plus x to the power n. So remember the first term should always be 1. So if I am able to express it in the form of 1 plus x to the power n, I can use this kind of a formula. And this is applicable only for fractional or negative powers. Right? So, for example, let's say if someone is asking me to expand root of 1 minus 2x. What is this root of 1 minus 2x? I can very well write it as 1 minus 2x to the power half. So, it is a fractional. So, in this case, I can very well use this expansion of 1 plus x to the power n. So, what is that? 1. So, x is for me is minus 2x. Only the first part should be 1. If it is not 1, I have to adjust it. Okay, the first part is 1. Okay, then my x is minus 2x in this case and n is 1 by 2. So just remember the expansion. And this expansion is nothing but, okay, you see the first term is x, then is x squared, then is x cubed, fair enough. Then you have n into n minus 1 by 2 factorial, n into n minus 1 into n minus 2 by 3 factorial, which is nothing but nc1, nc2, nc3 if you directly look at it. nc1 is n, nc2 is n into n minus 1 by 2 factorial, right? Because nc2 is nothing but n factorial by n minus 2 factorial into 2 factorial. And n factorial, as we have seen in our earlier chapter, I can write it as n into n minus 1 into n minus 2 factorial. So I just Strike this off, n into n minus 1 by 2 factorial. So it's nothing but 1 plus nc1 into x plus nc2 into x squared plus nc3 into x cube plus so on. But the only difference is I don't want to use nc1, nc2 there, because we are talking of that nc1, nc2, they are applicable only when n is integer. But the expansion is the same. N into n minus 1 by 2 factorial, n into n minus 1 into n minus 2 by 3 factorial, and so on. So this becomes n into x. This is the second term. Then I'll write it as n into n minus 1 into by 2 factorial into x squared minus 2x squared. So simplification you should be taking care of. Now if I want x cube term, I know that it should be whole cube. So whole cube means I should write it as 3 terms, n, n minus 1, n minus 2. So I'll write it as half, half minus 1, which is minus half, half minus 2, minus 3 by 2 into x cube minus 2x whole cube divided by 3 factorial 6. You expand this and whatever the value you get is the coefficient of x cube. So you should be comfortable in terms of solving these kind of expansions, especially when you get an expansion in the form of a plus b to the power n, where n is a positive integer. You need to follow one kind of a process. If n is not a positive integer, it's a negative or a fraction, you can follow the 1 plus x to the power n kind of an expansion, where you can look at the expansion of 1 plus nx plus n into n minus 1 by 2 factorial into x squared plus so on. And you should, and most common question in all these things is find the coefficient of something in the expansion of a particular expression. So you should be able to find out a coefficient of that, and that is what will simplify your analysis for you. So that is what is covered as a part of this particular chapter. Any further queries you have in terms of either the progressions or the standard summations or geometric mean, arithmetic mean kind of stuff, or writing them in the summation in the form of sigma or pi notations, or even the binomial expansion, I suggest that you can give me a call on the number which I have displayed below, 98480-12123. You can even email me your doubts and clarifications on my email address, vamsidhar@pacegurus.com. I request you to visit my website www.pacegurus.com for further updates regarding the training and consulting assignments we do in the area of finance, analytics, and actuaries using tools like Excel, SPSS, and VBA. I hope this session gave you some level of insight in terms of understanding the algebraic part required for your ASET. Thanks a lot for listening to this session. Thank you very much.